Section 17.10 discusses multiple reactions. When we solve multiple reactions, we do not sum the reactions together. We have to treat the reaction equilibria simultaneously using equilibrium constraints for each of the reactions. In this example, we have the two reactions shown with their equilibrium constants. The textbook shows a solution that would be obtained by hand calculations. In this screencast, I will show how to set up the solution using Excel. This set of reactions is known as a series parallel reaction set. It is a series reaction for component C because component C is produced by the first reaction but consumed by the second. The reaction is parallel for component A. This is because component A is consumed by both the reactions. The equilibrium constant for the first reaction is written in terms of partial pressures as shown here. Notice that the pressure has been written explicitly, but it will drop out of the expression. This reaction is unaffected by pressure. There are 2 moles of gas phase reactants and 2 moles of gas phase products. Here is the equilibrium constant for the second reaction. This reaction also has 2 moles of gas reactants and 2 moles of gas products, so it will also be independent of pressure. I need to convert feed conditions to mole fractions so that they can be used in the equilibrium constant expressions. I always set up a stoichiometry table. Here are the feed conditions. I'm going to keep track of the reaction progress using a reaction coordinate for each of the reactions. Now I proceed down the table writing balances for each of the species. For component A, 2 moles enter and it is consumed by both of the reactions with a stoichiometric number of -1 for each of the reactions. Component B is consumed by the first reaction only. Component C is interesting because it is produced by the first reaction and consumed by the second. There is no component C in the feed. Thus the only way component E is formed is after some C has been formed from the first reaction. Component D is formed only in the first reaction. Component E is formed only in the second reaction with a stoichiometric number of +2. I sum the moles in the feed and the products. Now I'm ready to calculate mole fractions. This is easy because there are always 3 moles of products. I simply take the moles for component A and divide by 3. Here are the formulas for the other components. Now I'm ready to insert the mole fractions into the equilibrium constant. And I'll do that on the next slide. Here is the expression for the first equilibrium constant. I have simply inserted the mole fractions. Remember that pressure drops out. Here is the expression for the second equilibrium constant. Microsoft Excel is not very good at solving for unknowns if I try to solve simultaneously for equations 1 and 2 as written here. I need to rearrange these for a reliable solution from Excel. I simply multiply across by the denominator and then move everything to one side, creating an objective function that should go to 0. I will call this obj1. I repeat the same type of manipulation for the second reaction, and I call that obj2. Here is the strategy that I will use for Excel. I will create a table with values for the equilibrium constants and for the reaction coordinate variables. I will enter a formula for obj1 and also for obj2, and then I'll solve. So here's the beginning of the spreadsheet. I've entered cells for K1, K2, the reaction coordinates, and the objective functions. I'm going to rename or change the font on X so that it looks prettier. I'm going to make it a symbol font. Alright, I'll do the same thing for component 2. I'm going to use cell names to make the programming easier. I'm less likely to make a mistake if I use cell names. Because KA1 is a valid name for a cell, I cannot use that as a variable name. However, I will append a period to create a valid variable name. I choose a period because it's easy to type in a formula and it can still be read quickly. To name a variable, I just type it into this cell after putting the cursor in the right cell. I'm going to call this KA1 period, and this cell KA2 period. And I'll call this X1 period and X2 period. And now I have a drop-down box, and if I want to find a variable, I can jump to that variable. Alright, let me enter the formula for the objective function. Alright, I just start typing the names. KA1 times 2 minus C1 minus C2 times 1 minus C1 minus C1 minus C2 times C1. And I just press enter. I'll do the same thing to enter the objective for 2. Alright, I've entered that, and I just press the enter key. I'm going to start with initial guesses for squiggle 1 and squiggle 2 of 0. If I have trouble, I can come back and try either initial values here, or I can adjust the way solver works. If I look at the material balance, I can see that both squiggle values must be positive, here and here, and I can see that squiggle 2 must be less than squiggle 1. The upper limit for squiggle 1 is the value of unity. I can use these constraints if I have trouble using solver. Let's pull up solver, and I'm going to set the objective function, and I can choose either of these. I'll choose the first. I'm going to set it to a value of 0 by changing both values of squiggle. I'm going to set it to a constraint. I'll choose change here. I'm going to set this constraint to be equal to 0. I can make them non-negative. I'll leave that checked, and I click solve. Solver did find a solution, and it thinks it's okay. If I check the answer, I will find that agrees with the textbook.